Okay, I think it's 5:30. So welcome back, everybody who made it back. We're very sorry, apologize for the technical difficulties. Somehow there must have been a server hiccup somewhere. And Klaus agreed to give his full talk again. So we're going to not lose anything except for Ofer's very nice introduction. I'm going to jump right back in and hand the word over to Klaus. Thank you.
Thank you very much, Sebastian. And even though some of you maybe did not hear Ofer's nice introduction, I want to acknowledge it and thank you very much, Ofer, for the kind words. It brought back nice memories of my early work in science. And at that time, I was younger and I lived a different life than today. The topic I will discuss today is actually a scientific question that I also asked myself 25 years ago. And I didn't know the answer at that time. And I think if there's a lesson of this talk, apart from the physics, if you're a young student and you feel that something is difficult to understand, then maybe you cannot find the answer. And maybe it's not you being right or the lecturer being right or wrong, but remember it, because maybe 15 or 20 years downstream, you will realize that that question could have some influence or could inspire work that you are doing at this time. I'll be talking about light that moves. I will talk about quantum light that moves, and I will discuss with you how that actually requires a new description compared to a lot of the quantum optics theory that we have in our textbooks today. The work is foundational in terms of quantum optics, but of course it's also highly relevant because we are using light that moves as a messenger to transport quantum information between different locations. When I made this slide, I had of course in mind the quantum internet with different nodes connected by optical fibers. I realized that maybe this is as much a picture of us as a community sitting in our different cities and listening to each other give talks via the internet and connection. There are different modalities, there are different ways to connect physical entities by light or microwaves or acoustic waves, and some of them do not need the theory I will describe today. I'll be talking about something equivalent to what you have in mind as a flying qubit, that you take a quantum state, you pack it into a pulse of radiation, and you send it somewhere, and then when it arrives, you can store it or you can process it in some way. And I'll show you that needs a special theory that I hope you will like to see. It's not super complicated, but it's kind of interesting. The work has been developed in connection with two projects we are working on. There's a project sponsored by the US Army Research Office with Mark Safman, where we're dealing with neutral atoms. We can do local Rydberg interaction gates between neutral atoms, but if you want a scalable design, you might want to have another trap next door where you also have an ensemble of Rydberg atoms, and you may want to use fibers to connect quantum information between such sub-registers of a larger device. And there's a similar project not using Rydberg atoms, but ions in crystals called SQUARE under the Quantum Flagship program. And in that program, we also have an idea to reach scalability by putting our crystals inside cavities and connect them by fibers. Okay, but with that, let's move into the talk. In quantum optics systems like atoms and ions, we have quantum states that we store in more or less stationary quantities, but we also have the possibility to use traveling fields, laser fields, for example, or pulses of few photons to communicate quantum states between atoms or ions. And there's a huge effort going in that direction. There's also the modern competitors to quantum information technologies, what I call the bits and pieces, the devices we built ourselves, superconducting qubits or quantum dot designs, where we also need this ability to couple. And some of these systems have excitation frequencies in the microwave regime, and therefore these might be coupled by microwave waveguides. The lower picture down here in the middle is actually suggesting a piezoelectric coupling, where the qubit talks to a surface acoustic wave that propagates to other components on the same chip. It's very, very exciting new prospect to transmit quantum information. In all these systems, you can say that we have dealing with stationary qubits, the physical material system, and then the waves that we use to transmit quantum states. And this is exactly what I want to talk about. From a more foundational point of view, let's jump all the way back to Maxwell equations. This is the theory of light. As it's written here, it's the classical theory of light. But as soon as we quantized the electron motion, then the charge density and the currents actually become quantum mechanical. It's a bit like the coronavirus. If part of your system gets infected with something, then it quickly spreads to everything else. So you cannot have non-commuting quantities on the right-hand side of the Maxwell equations without some of that lack of commutating properties will also spread to the left-hand side. If these are operators, the left-hand side have to be operators too. And in fact, the quantum theory of light is exactly the same equations as you see here, just admitting to the fact that the B and the E field, the electric and magnetic fields, become operators. So the fields are quantum observables, and they obey some of the mathematical properties we know in quantum mechanics. In fact, the Maxwell equations in this way becomes equivalent or become the Heisenberg equations of motion for the field operators, and that is how we quantize the radiation field. Now, we also talk sometimes about states of light, and when you talk about a quantum state, you're not talking about observables, you're talking about wave functions or density matrices. So that's a different representation. It's the Schrödinger representation of quantum mechanics. And that means that we are not going to talk about A and A dagger or the number operator. We're going to talk about states of the field, maybe with a certain number of photons in them. So a Fock or a number state, a state with n photons or 5 photons, refers to a field which contains those 5 photons. And that can be the optical field between 2 dielectric mirrors, or it can be a microwave field contained in this microwave box that will confine such a field. So what that number actually refers to is the number of excitations, the degree of excitation of a particular mode of the electromagnetic field, a standing wave mode typically in these settings. There are also other states. There are superpositions of the Fock states, the coherent state, which is a superposition which has a very particular property, namely that the Q and P, equivalent to position momentum of harmonic oscillators, they have a minimum uncertainty between them. It looks like the ground state of the harmonic oscillator, which has been displaced, and in the field units, it's like the electric and field quadratures being in a minimum uncertainty state allowed by quantum mechanics. Again, this is a description in terms of the number states or the coherent states of a single mode of the field. So we are not referring to a field that propagates, we're referring to maybe a standing wave of a particular frequency and wave number in this cavity. We can also interact with these fields. This is a picture of the famous James-Cummings model, where I'm sending a 2-level system through a cavity, and if there's a resonant interaction, the atomic excitation energy is equal to the photon energy, then you can have a coupling between the two, and this atom might leave the cavity with a photon more added to the field because the energy has been transferred between those two. Then for completeness, we might remember the atom can also decay into other directions, and we might also have the cavity decay, but the fundamental description of this is like a quantum mechanical entangled state, wave function or state vector containing both atomic components and field components. But again, of course, I'm here talking about a single stationary standing wave of the electromagnetic field who contains the relevant number of photons. So the small print in your quantum optics textbook is that when we see all these beautiful pictures of coherent states and sometimes squeezed states, then this description refers to a single mode of the field. It does not refer to a traveling beam of light. Traveling beam of light is a different thing. It's a single mode. Doesn't have to be a standing wave, but if you want to do this experiment in practice, this is often what we have in mind. In fact, you might see in a few minutes how I will deal with this kind of description, but of pulses which are moving and how such pulses interact with matter. And it's not going to be the James-Cummings model. A beam of light is something that looks like this. This is light that keeps coming. This is like the electromagnetic field, where your classical picture, what is a field, is of course that it's something that extends through space. And if you put up a detector, you will see it keeping coming towards the detector. You will get a signal over time. And such a field is generically multimode. I put down these vertical yellow bars just to indicate that you could think about every one of these little segments to be the quantized single mode we talked about before. There could be 0 photon in this first slice, or 1 or 2 photons. There could also be both 0, 1, and 2 photons here and here and here. So the Hilbert space is the one of many oscillators, because every slice of this beam is like one of the modes that you see in this upper part of the figure. So the small print in the quantum optics textbook is that when you come to describe beams of light, you actually have many, many modes. And it's of course an open, not an open question, but it is a question you can ask yourself. how many of these pictures actually describe the situation of a beam arriving to your detector? So the Schrödinger picture in general of a beam of light is going to be super complicated, because there's going to be potentially an expansion on number states, but that will be an expansion in every one of these slices. It's what makes quantum field theory hard, is that you actually have the possibility to excite all these different field degrees of freedom. It's practically impossible, I would say, for many light sources to give a Schrödinger description of the radiation coming from your light source. It's a little bit like having the cake that you cut into slices up here. If you want to know about some property, then you would say, well, you have to account whether it's sitting in the first slice, the second slice, the third slice, and all of these have their own independent description, or even worse, might be in an entangled state with each other. So you have a really complicated description of this beam situation. What we typically do, and that's what happens in about the middle of your quantum optics textbook, is that it comes to chapters to describe lasers and OPOs and sources of light, which are emitted as beams. And that is that these books typically switch to the Heisenberg picture. They give you a description of properties of the field observables. They tell you what is the mean field. They tell you what is the mean intensity. And in fact, you can also tell what are correlation functions between the field at different locations inside this beam. For example, if you look at fluorescence from a single two-level atom, it's a monstrous quantum state of light. But if I know that this is a light source who can emit photons by spontaneous emission, I can actually calculate the properties of this beam. The mean intensity is given by the mean excited state probability of the atom, because there's a decay rate associated with this atom. And if I want to know correlation functions of the signal, the spectrum of the signal, then we also know that as soon as you have an equation for the source, which is the master equation for the atom, then when I solve this master equation, I can also get access to all these correlation functions. The emitted field is proportional to the damping term in this Lindblad master equation, and that damping term is the lowering operator for this atom, the atom jumping to the ground state, and the two-time correlation function of this Pauli lowering operator, raising operators, is actually the same as the two-time correlation function of the signal in the beam. So this is the standard analysis, and this is what we have been doing for decades to describe these light fields. And I just remind you again, this is not a Schrödinger representation of this field. The description of the interaction between this field and any obstacle that it may meet along the way is going to be complicated, because we don't have a wave function for the field, but we have a Heisenberg description of the field. And of course, there are many, many situations where that suffices, and great theory exists. I would not say that the literature is full of errors, people doing this wrong. I would say we found the different problems that we could solve with the tools. But I'm just super interested in this talk in actually making a Schrödinger picture description of a light pulse that interacts with a quantum system. So can I have my cake and eat it too? I think that doesn't make any sense, except that there's a cake in this picture. But I really want to describe a quantum field of light that occupies a single pulse, and that's actually a single mode. So the Hilbert space should be limited in size, but the problem is, of course, that such a pulse traveling through space might not be the same as a standing wave sitting between two cavity mirrors. So here is a picture of a pulse of light, and what I show you here is just the classical mode function. So this u of t is an eigen, or not an eigensolution, sorry, it's a wave packet that is describing a solution to Maxwell's equations. It's propagating with the speed of light along this kind of waveguide you see here. So when you have solved the classical wave equation, then you can start filling photons into that one, the same way as you could with the eigenmodes of the Maxwell theory. So second quantization says you can equip such a pulse with 5 photons or 11 photons, and that actually just means that there are precisely that number of photons who are all sharing that particular mode function sitting here. You can also define a creation operator, which is just the weighted integral with this u of t function of creation at time t of your particular photon. And you can create superposition state. So in fact, we do have a Schrödinger description. We have a state vector description of the content of light pulses, just the same way as we have for a standing wave mode. We just have to remember the dynamics, that it's maybe the photon number doesn't change, but certainly the wave packet moves. And that's what we like about it, because that's why we use it in the first place, to communicate or transport things. So this kind of pulses are the ones we might prepare. And in fact, there are different schemes to use such pulses to drive a quantum system. They can be flying qubits prepared in superpositions of two orthogonal states to encode quantum information. They can also be used as probe pulses to probe a quantum system by the effect on the pulse of their interaction. You can also transport pure mixed states or transport even energy with these kind of wave packets. And as long as you're only propagating through a linear medium, there's actually not much happening. The U of t changes, the pulse travels, but the state remains the same. You are just moving your 5-photon state from side A to side B. But the problem is what happens when it arrives? How does that pulse interact with the quantum system that it's intended to actually meet and interact with? So here's a Schrödinger cat, a flying Schrödinger cat state, and we will now see, or maybe it's a Schrödinger kitten actually, how to describe this kind of systems. So here on the left, I show you the James-Cummings model. I show you an atom flying through a cavity mode. This gives you a time-dependent coupling because the atom talks to the field with a strength which is given by the wave, the shape of the electromagnetic wave. So there's going to be a time-dependent coupling just because you are exploring the regions with higher and higher value of the field mode, and then you are leaving again, going out, and the coupling goes to zero. Is that the same as the picture on the right, where I have a time-dependent pulse who is traveling past a two-level system? You would definitely say that there must be an interaction between the two, who is increasing and decreasing as the pulse, the mode shape is overlapping with the atom. But it's not the same. So the answer is no. And the answer is no because there's not only the exchange of quanta between the emitter and the field that you see in the picture on the left. There's also a distortion of the pulse. The traveling pulse on the right is actually occupying a mode continuum. All frequencies are allowed in the waveguide. There's not an energy gap to any other shape of that pulse. So when you interact with the atom, dispersion, for example, will change the shape of the pulse. And if there's some kind of nonlinearity, which you will see because of the two-level atom and saturation, then there will be a correlation between the shape of the outgoing pulse and the number of photons in the pulse. So there's a transformation of the shape of the pulse that happens when you have traveling pulses interacting with matter, while on the left-hand side, we always treat the mode function as constant in time. And that's because you are talking to a standing wave. There are also other standing waves in that cavity, but they are discrete modes. So therefore, they are spectrally gapped. And the reason we typically write only a single mode in the James-Cummings model is not because that's exact. It's because it's an approximation that the next mode is so far away in energy that you are not coupling efficiently to that mode. So if the coupling strength G is less than the free spectral range of this cavity, that is the frequency separation to the next mode, then the energy interaction is not strong enough to occupy any other mode. And what is happening on the right is just the opposite situation. Any weak interaction is capable of distorting the incoming pulse, and it's going to be in a complicated matter where both the photon content and the shape of the pulse will be altered in a complex way. So these two systems are not the same. In fact, there's also another difference, which is the same thing, and that is that on the left, the two-level system is only coupled to this particular mode in the cavity. There might be weak coupling to other dissipation channels, but if you look on the right, the atom is constantly coupled to this waveguide along which this pulse is actually propagating. And the coupling to a vacuum state along that waveguide is almost equally strong as the coupling to the one-photon state occupying that mode. The excited atom here is not only giving its energy back to that pulse, it actually decays by spontaneous emission along the waveguide. Part of that spontaneous emission will occupy a shape which may be similar to the incident pulse here, but part of that may just be like normal fluorescence, occupying a whole continuum of frequencies, and that's really the problem we have to look at. The system is, as I write here, an open quantum system because your system is coupled to a continuum of frequencies, which is disregarded in the James-Cummings model. So that's the problem. Now we have to solve it. And I'm going to solve it by inspiration from work on what's called cascaded quantum systems or cascaded system master equations. There were two papers back to back by Crispin Gardiner and Howard Carmichael in 1993. And the point of those papers was to describe quantum systems driven by the output from other quantum systems. So again, the challenge that I really feel is an urgent one in our field. How do you drive quantum systems with quantum fields? How do you solve that particular problem? And in fact, they solved it not with the purpose of describing pulses, but actually putting maybe another atom here and see how the fluorescence from one atom is driving and exciting its neighbor atom. A real solution to the problem I've been posing so far came, as I know, for the first time in 2012 by Josh Combs and first author Ben Baragiola. And that was really a beautiful paper. And I was jumping up and down when I saw it, because I felt that this theory was missing. And they actually offer a theory for how an n-photon wave packet interacts with an arbitrary quantum system. I will give you a theory who solves exactly the same problem now. My theory is a little bit more straightforward. I'm actually going to give you a completely normal master equation, while their theory is a kind of hybrid Heisenberg picture where they give you moments of certain observables. And I will also extend my theory to actually describe the content of pulses leaving the system, which I think is difficult in this theory. But it's a beautiful paper, and it's really the reason that we made the progress that I'm telling you about today. So how does a quantum pulse interact, for example, with a qubit? So we had a paper that came out in the late fall, and this is really the challenge. It's this two-level system, decaying by spontaneous emission, being hit from the left by a pulse of radiation containing some arbitrary quantum state. Here's a trick. So I don't really like to solve Maxwell's equations. I would like to replace this by something that I can handle more easily. And you know, a pulse is actually not so difficult. If I have a cavity with a time-dependent output coupling, then I can make any content of such a cavity leave the cavity with exactly the shape that I want. This is linear optics. So if there's a 5-photon state in a cavity and I leak with a certain transmission amplitude, then I will populate a mode function which is given by exactly that amplitude. Imagine that you suddenly switch off decay with a constant amplitude, then the cavity will decay exponentially. So you're going to see an exponential tail of light coming out of your cavity. If you want it to look any different, for example, like a Gaussian pulse, then you have to modulate this G, turn it on swiftly, and then keep turning it on, and finally turning it off again. So you just got the shape you like here. It's a problem of purely classical optics. It's a simple differential equation. And in fact, I couldn't resist from just putting it here. The amplitude has to be related to the field you want. But since the cavity field is losing power, then here I'm actually dividing by the cavity amplitude. That's 1 minus the integral of the field who has been lost in intensity. So by just adjusting the outcoupling like this, you will get a field pulse coming out which has the shape you like. And why is this a trick? Well, it's a trick because I will completely eliminate this waveguide. I'm just going to couple the two-level system here to this cavity by the field that leaks out of the cavity and drives my system. So I have a single mode cavity, and I have an atom, and I have the interaction between the two by exchange of excitation. So you can see that what is going to happen now is that I have here my Hamiltonian. I can remove a photon from the cavity, and that photon has gone into the pulse, but it's going to be absorbed then by the two-level system and the Hermitian conjugate. And maybe the first funny observation here is that it's not the U function sitting here. It's actually this funny outcoupling strength that tells what is the coupling between those two systems. In addition to the Hamiltonian coupling between the two, I also have damping, because there's a whole waveguide open with modes here where you can have light leaking. And any photons you see out here could actually be a superposition of the dipole emission from this atom, or it could be just the photon coming from the cavity passing by the atom. So what you see here is actually that superposition formula. The field you see is a superposition of the field leaking from the cavity and the field emitted by your two-level system. This is an equation reminiscent of the classical optics Ewald extinction theorem, who tells you that the electromagnetic field is always the freely propagating field plus whatever is emitted by the sources. Sometimes these sources can be in destructive interference. That's when this leads to absorption. Sometimes they can be out of phase. That's when it leads to dispersion. And what I'm just noting here is that this field leaking out here is a superposition of these two terms. If I see a photon, I don't know if it came from the atom or if it came from the cavity. And this is the damping operator sitting in my master equation, because this is a loss channel. Right? This is excitation, which is no longer in the cavity, no longer in the atom, but is propagating along the waveguide. So what I get is actually a master equation with this Hamiltonian and this damping term. So here is the typical form of the master equation. There's a commutator with the Hamiltonian, there is this structure, it's called the Lindblad master equation, and master equations typically have this form. If you had only a single two-level atom, there would be only the step-down operator here, and that would give you the usual optical block equation. But in this case, the damping is actually correlating those two systems with each other. At a formal level, you will also notice an interesting thing, because in the Hamiltonian, you have these terms, for example, A dagger sigma, which is the transfer of energy between the two systems. In the master equation, you have L dagger L, and that will give you cross terms of the same time. You will have an A dagger from L dagger, and you will have sigma from L. So you're actually going to find an A dagger sigma on the left of the row here, both from the damping term and from the Hamiltonian. And magically, those two will cancel. So when I write down the equations, just all the terms, I'm going to get this equation. Now, on a computer, I'm perfectly satisfied with the first line, but I just write it in this funny way, which has this different appearance, where it seems that the dissipation is just a purely atomic decay, purely cavity decay, as you would have expected them to look. And then you have this term, which is really not the commutator with the Hamiltonian. This is not representing unitary evolution. It's mixed up together with the dissipation part. And what you notice in particular is that on the left from A, on row here, you are acting with the annihilation operator of the field, annihilation, and never with A dagger from the left of the density matrix. That means there's actually no photons being created in the pulse from this interaction. There's only light moving to the right. So the Hamiltonian is chiral in a sense. The light is moving from the left to the right in this picture. And even though the Hermitian Hamiltonian has excitations going both towards the right here, but also to the left here, they actually cancelled by this interference of the damping term, so that excitations move to the right, as I show you here. It also has another consequence, namely that the cavity alone actually has a separable density matrix. The cavity itself is just being damped by this term, and that's all that happens to the cavity field. It goes towards the vacuum state when the pulse is being completely emitted, and that actually also means that this pulse is going to disappear, obviously, because it's going to fly into the atom and disappear, because we are not interested in what is sitting on the right of this particular atom. So my theory here is giving me a master equation, and here it is, and I can actually just go ahead and solve it. And it's not the same as the James-Cummings model. If the input cavity field is in a coherent state, then it's interesting, because then the master equation will actually just give you a damped coherent state. So the cavity is just being damped, and it's going to be weaker and weaker classical field. And that actually means that I can put this classical field into my equation, and I get a closed equation for the purely atomic master equation. So the two-level system is now damped, and then it's going to be driven by the field, who is the field mode, times this initial amplitude. So this is a classical drive of the atom by a classical field whose shape is exactly the shape of the pulse. So if you thought that a classical field should be described just by a C number varying in time as the pulse, you are right. The two-level atom is exactly described like that, and this is the correct description when you talk to a coherent state, which is pretty amazing actually, because you may remember that if you are in the James-Cummings model, a coherent state is more complicated. It has Rabi oscillations back and forth with the atom at different frequencies, because the different Fock states have different coupling strengths to the two-level system. An input Fock state, in my case, is difficult to solve, because the state here is not going in a simple progression. The cavity is leaking, and it becomes a mixture of different Fock states, and you have to keep track of that correlation between the two systems. So there's really big differences between the dynamics of the pulse talking to the mode, or the system, sorry, and the cavity standing wave talking to a two-level system. So what about the state of the pulse after the interaction? Well, there is no pulse after the interaction in this picture, but of course I could ask myself, what is the state content in some particular mode that I just picked because I'm interested in what is the content of this thing. So this is a single mode, and because it's a single mode, the quantum description of that in a Schrödinger representation is just like a single harmonic oscillator. And if I would like to know what is the content of this particular mode, then I should find a way to analyze that. You might hope that maybe this incident pulse has almost all the light coming out in a particular mode, which has been slightly distorted, dispersed by the interaction. And the same way as I could create an input pulse from an artificial cavity. Of course, this is just a theory construction. The real experiment is, of course, the true pulse. The analysis of an outgoing pulse can be done with an analysis cavity. So just imagine you put a cavity with a GV of t in coupling strength such that it would precisely absorb the V of t wave packet. Then instead of having this continuum description, I now have a discrete system of 3 components. Here's the shape of this GV to make it work. And the cascaded master equation says you have an oscillator, 2-level system, and another oscillator describing your output pulse. So it's not a James Cummings model with an oscillator and a cavity. It's actually an extended model with 2 cavities and a 2-level system, the U cavity, the V cavity, and the qubit. And I remind you again, this is not for the experiment. The experiment looks like this, but the theorist can describe this whole system by a discrete master equation with these 3 discrete systems. So you can, of course, put more than 2-level atoms. You can put an arbitrary scatterer and damping terms on the scatterer too, and then you just get a more complicated master equation. So I made a little table here saying that you can have a quantum input pulse, you can have a quantum scatterer. If you don't care about the output, then you just have to solve a density matrix for the 2. You can have actually a scatterer who produces an interesting pulse, but you're not driving it with anything quantum, but just drive it classically. And then you get a quantum density matrix for the system and the outgoing pulse. Or you can do the full structure here with an incoming pulse, scatter, and outgoing pulse. And then you have to solve this 3 discrete component density matrix. And here is the full master equation in the full case. It contains exactly what you would expect, kind of flip-flop interaction where excitations are going back and forth. And then this interfering term of everything that even leaves the last V cavity. Again, if you mix these terms together and you just write them out, you'll find you have this chiral property again. All the excitations move from left to right, from that cavity to that system to that cavity, and then something is lost in the end. So this is where I'm willing to take a few questions on the method, and then I will show you a number of examples.
That's great. Well, thank you very much, Klaus. It's been very interesting so far, and we've got a couple of questions that have come through in the chat. The first one this week is from Bill Phillips, who asks, one sometimes hears that there is no such thing as the wave function of a photon, but you seem to be describing just that. Can you say something about this?
Yes, I can just briefly. Hi, Bill, it's good to see you, or good to talk to you. I mean, there is a wave solution to the Maxwell theory. And I particularly favor the theory of Ivo Birula from Poland, Warsaw, who some years ago pointed out very clearly that the Maxwell equations is actually the same as the Dirac equation of a spin-1 zero mass particle. If you solve that Dirac equation, you get exactly the E and the B field as components of a spinor type wave function. And I think that's the wave function of the photon. Of course, I know that the great scientists, very great scientists, have told what are the issues with such a thing. It doesn't describe a probability density. And in fact, it doesn't, because since it's the E and B fields who are the wave function amplitudes, it rather describes E squared plus B squared, which is the energy density. But I think it's fair to think about the wave packet as the wave function of the photon. And second quantization is telling how many particles are in that wave packet. The same way as you, Bill, it's actually putting atoms into a Bose condensate, and you have your Gross-Pitaevsky wave function, and you can put as many atoms as you like into that one.
So the second question comes from Michael Gera, who asks, can you really generate any pulse, or do you have constraints given by the coupling strength and the Born-Markov approximation?
Yes, that's a super good question. In fact, I'm assuming the Born-Markov approximation, and that will be wrong if you have super fast dynamics going on in your system compared to the bandwidth of the reservoir. And in fact, it's fair to say, no, we cannot deal with that situation. Then our model is not good enough.
Okay, and maybe we take one more at this point. So the next question is from Inigo Arizola, who asks, can you recover Rayleigh scattering in some limit in this theory?
Yes. Okay, super good question. Thank you very much. Rayleigh scattering is actually when you look at this lowering operator sitting down here, that guy's going to have both a mean value and of course fluctuations. And the mean value of this term, which is driven by the incoming field, is actually what corresponds to the Rayleigh scattering. It's coherent with the drive, and that is what characterizes Rayleigh scattering. So Rayleigh scattering is the one described by the mean dipole, and that's also part of this theory.
Okay, so we'll have a few more questions at the end. I see a few more popping up in the chat, but I think we should let you continue, Klaus, and come back to those later on.
Thank you very much. So I'll give you just a few simple examples of this theory. So let me do one which is trivial and can be solved in many, many other ways, namely a single photon scattering on an empty cavity. Okay, this is a linear optics problem. There's absolutely no reason to use my theory. I just show you how it works. So there's an input wave packet u of t. I know how to construct this g function, and there's going to be an output wave packet, and I know what it is because I can solve scattering on an empty cavity. So I know what is the v of t, who's going to contain all the light coming out, and therefore I can also calculate this gv function. In fact, if you come in with a Gaussian pulse like this, then the outgoing pulse will have this particular shape, and that's of course due to the dispersive interaction with the cavity. Now, we describe it with two oscillators and the empty cavity, which is a third oscillator. So in fact, I have three oscillators here, and initially I had one photon in the first oscillator. What is shown here is the mean excitation of the cavity during the scattering. The photon leaves the first oscillator. I have a temporary excitation, and then this outgoing light is the one who is eventually piling up into this particular V mode you see up here. So I have managed, and of course it's easy, I managed to transfer a one photon Fock state from an incoming pulse to the outgoing pulse. And meanwhile, I was sort of populating all of these artificial cavities, but in the end, I had this result that I like. Now, that was too easy. So let me make it a little bit harder, and let me put a shaking mirror in the cavity. So you know, if you have a shaking mirror, that's going to add frequency components, decoherence to the system. The output is going to be generically multimode. It's not going to be a single coherent pulse coming out. And might be a dominant output mode. So you might look for that and ask, where is most of the photons actually sitting? So here is a alpha equal to 2 coherent input state. So what I show is the mean number of photons 4 in the incoming cavity, and it leaks and leaks and leaks. The pulse is not there anymore. And then I have taken what I thought would be the best outgoing mode, and then I look at the population of that one. And it goes all the way up to almost 2. So I have about 50% recovery in that particular mode. What is shown in the insert is the initial coherent state circle uncertainty, this Heisenberg uncertainty here. And this is a weaker field coming out. And this banana shape or croissant shape comes from the dephasing. So there's a phase uncertainty, which is larger here because of the shaking mirror. But it has only about half the photons. Where are the other half of the photons? Where they are, of course, occupying other modes because the output is multimode. So this theory does not give you the full quantum field leaving the cavity. It gives you the full quantum state of any mode function you like leaving the cavity. And since the application for flying qubits will typically be the interest in what we could fit into one particular mode, or maybe a few, then this is the theory for that kind of questions. But it's not the full quantum field theory that I'm presenting to you here. Here's another example that I really like. That's the process of stimulated emission. So if I have an excited atom and I hit it with a pulse with one photon, then you might dream of a process in which the atom jumps to the ground state and the pulse is leaving the system, but now with 2 photons inside of it. And that's indeed easy to do in the James Cummings model, because that's going to be 1/2 Rabi cycle, where the excitation goes from the 1 photon excited state to the 2 photon ground state component of the system. But remember that this atom, while happily talking to this photon field, it also decays into all other modes. And it may even eat some of that 1 photon and also disperse that into other modes. So we calculated this with an incoming pulse, and we find that an incoming pulse with 1 photon is leaking, as it should. And this is actually the n equal to 2 component in the best possible outgoing mode. And you see that that population goes from 0 up to almost 1. So stimulated emission worked with 96% probability here. So we actually did obtain this stimulated emission process that I was aiming for. And of course, this is an interesting optimal control problem. What is the best shape of this pulse so that this process is going to have the highest possible probability? And there's nice work by Fisher, who is suggesting what shape you should use. And in fact, the higher the incident photon number, the more effective is the stimulated emission. So this process of stimulated emission can be a very efficient process, even with the pulse going on here. Schrödinger's cat. There's a very nice experiment, recent experiment by Gerhard Rampe at MPQ, where he puts a two-level atom into a cavity, and depending on the state of that two-level atom, the atom will interact with the cavity field. And that means that a pulse who will enter here will either experience with one atomic state a direct reflection, because you're not allowed to enter the cavity, or if there's no interaction, the pulse may be perfectly resonant with the cavity, so you do enter and get reflected. And that has a net effect of putting a relative change of sign on your coherent state amplitude. So the atomic state controls the phase of the emitted coherent state. So you get an entangled state where one atomic state or the other atomic state is accompanied by the coherent state or the minus amplitude coherent state. So this is the beautiful idea. And what is you have to remember in this process is that this is a wave packet. It's not only a coherent state in a mode like the James-Cummings model. That wave packet also changes its shape. And it may change its shape in a different manner depending on whether you are allowed to enter or not enter the cavity. So we solved the equations and we confirmed actually pretty good agreement with this beautiful experiment that there is a high fidelity. This is a Wigner function portrait of the field leaving this cavity where you herald on measuring one of the atomic states. And you can see that there are definitely these characteristic fringes. If you did a stronger coherent state, you would see these fringes more clearly. If you ignore some of the dissipative mechanisms, it's good to be a theorist, then you will see these fringes even better, of course. But a main contributor to the infidelity of the cat is not so much the loss here, it's actually the reshaping of the wave packet and the mismatch of the two wave packets. I could define the cat a little more broadly, being not only alpha and minus alpha, but being alpha in one spatial shape and minus alpha in another one. And that is, of course, also very catty-like. And then my fidelity for that kind of state would be higher, because then that's what you get. So this is what we can do. And of course, again, the numerical calculation is a density matrix, which is just mapping an oscillator containing up to the relevant number of photons. Then the system here, which is a two-level in a cavity, a two-level atom in a cavity, and the outgoing pulse, which also has to contain all the photons which are present in the input field. Now, I need to tell you about one of the important physical consequences of this interaction with pulses, where we differ significantly from cavity QED. What I show you here is a beautiful proposal by, I think, Jeff Kimball and others have had similar proposals for an effect called photon blockade. So the photon blockade idea is that if you have a cavity with two-level atoms inside, then the James-Cummings interaction is going to give you so-called Brest eigenstates. So I can have the atom in the ground state at no photon, and then if I actually try to drive the cavity, the eigenstates are not at the cavity resonance, but at these Brest states, which are superpositions of the atom being excited and the cavity being excited. And they have a certain energy here, and if my photon is exactly on resonance with this Brest state, you will have perfect transmission through the cavity, because you excite that state and then it leaks out on the other side of the cavity. But two photons of the same frequency will not be resonant with anything. In the empty cavity, they would be resonant with the first process, but they would also be resonant with the next one. Because this James-Cummings ladder is not harmonic, you will have one photon being transmitted, but the two photon state would apparently not be transmitted because it's not resonant with the system. So the proposal would be that such a system would only allow pulses go through with one photon states and not higher photon numbers, a filter that magically turns weak states into single photon states. So here is one photon state being reflected. And what you see is actually, this is a function of the duration of the pulse, that if the pulse is very, very short, you have perfect reflection. And the reason you have perfect reflection is that an ultra short pulse is spectrally enormously broad. It doesn't even see that there's a cavity, because the cavity is a very narrow line and you cannot enter into that cavity. So if the width of the pulse in frequency is much wider than the cavity line width, you get perfect reflection. But if the pulse is longer, then you get good transition to transmission, because the pulse is resonant with the cavity, you enter the cavity and you get transmitted through the cavity. This is the single photon scheme and it works. Now the two photon state, well, the purpose of this was that we should see blocking. But what you see is actually very good transmission of two photons in this case. So you don't see any transmission for short pulses, but that's because everything is reflected for short pulses. But for the long pulses, that's exactly the regime where we expected the good transmission. And it doesn't happen. So why doesn't it happen? Well, it doesn't happen because we are not doing cavity QED with these cavity photons being standing wave photons. This is a pulse arriving, And the pulse, if it's short, is broad bandwidth, so nothing happens. If it's long in time, it's the narrow band. But in fact, the length of that pulse may be much longer than the interaction time of the photons with the cavity field. So if your pulse is longer than the lifetime of a photon in the cavity, that's the same as being spectrally narrower than the cavity line width, then your two photon state has a small overlap for the two photons being here at the same time, but most of the amplitude actually has the photons sitting at different places in this particular wave packet. So you could actually see sequential transmission of the photons, even though they enter in the same mode. When they leave, there will be an anti-bunching feature. So you will not be able to see the two photons right on top of each other, but they can still occupy this two photon state with very high amplitude. So I call it the photon bandwidth dilemma, that if you really want to have a very selective process talking to your photons, your pulse should be narrow in frequency, but then it gets long in time. And when it gets long in time, your photonic nonlinearities become inefficient. You don't have all the 5 photons or 2 photons talk to your nonlinear system at the same time. Think about James Cummings model. All the 5 photons in the James Cummings model talk to the 2-level system at the same time, because there's no way to escape. They all occupy the same mode. In this case, there's a way for these photons to be sequentially transmitted. So this is super exciting, I think. And I'd like to talk a little bit about the output mode, and then I have to wrap up. But we already spent 10 minutes on the first question, so I know I have a little extra time. I can see Andrew smiling. What is this output mode? Is that just something that I pick because I like that one? Well, like, it would be nice to have some guidance. Maybe in some processes, you actually only want to transform the quantum state content of the incoming pulse. So then you should pick the same U out here. That's what I did with the stimulated emission process. But sometimes you don't mind that the added photon to the field or the absorbed photon to the field made the transformation into a slightly changed pulse shape. As long as you know it, you can also deal with that one. And so the question is, of course, what guiding principle would we have to actually find the V given the U? So at least as a quantum optics person, I propose the following analysis. The full output field here is described by this decay operator. That's the equivalent to the field operator as function of time leaving this system. So I can actually determine the correlation function, the first order correlation function of this guy. This is the one whose Fourier transform is the spectrum of the emitted light. But as you write it here as a 2-time correlation function, it can actually be diagonalized as if it was a matrix, or it can be mode decomposed into a sum of modes Vi of t with weight factors Ni. And these weight factors is nothing but the photon occupation number in those particular modes Vi. So this is a quantity we can calculate without bothering about the output field. So I just solved the first 2 component systems to find what is this correlation function. Then I diagonalize it, find the eigenmode with the highest occupation, and that would be the candidate for where your interesting pulse is sitting. And it will also tell you what is the shape, and so any dispersive change of this one or any absorptive change of that one will now be part of the calculation. So this is actually what we did when we had the shaking mirror. So this is the G1 function for the shaking mirror, and if I diagonalize that G1 function, then I find these 4 modes, I find 11 modes, I find 100 modes if you like, but I find one occupied by about 50%. The second one, who looks like this, the red curve, has 26%, 13%, 17%, etc. So you have this possibility to actually calculate candidates for which are the good modes. Maybe it's not the power you want to maximize. Maybe you want to maximize the negativity of a Wigner function or any other crazy thing you like in quantum optics. And then it would be a different challenge to do your, say, optimal control theory, vary this V to optimize that particular function. I'll let you have your own preference on what you want to maximize in your output field. I think it takes me to the end of my talk. So my conclusion, I think quantum optical systems and many of these new bits and piece systems, they compete for attention as oh, what is this? This is the conclusion of a wrong talk. Sorry about that. Okay, so quick job, too far job. The conclusion of this talk. Sometimes photons move, and that's exactly what we like about them, right? I mean, that's the key application of the photons or microwave photons. And of course, you can see what I talked about here could have been phonons in acoustic waves too. And that motion means that when we interact with them, we have to interact with a continuum in which they are propagating. Moving photons or phonons occupy a continuum of modes. Their quantum states and their dynamics are highly non-trivial. The quantum information protocols rely on the precise handling of these modes. If you say that my quantum information is stored in a particular mode, then of course if that is transformed due to the interaction with your stationary qubits, you need to know about that transformation. You need to know where did the excitation of your stationary qubit actually go when it was emitted as radiation. If we may restrict our analysis to a few incident and a few outgoing traveling modes, who are all solutions of the Maxwell equations or the wave equations, then we can apply a master equation theory in the usual sense of few modes, and therefore numerically, of course, this has become a tractable problem. This is not the full solution to the multi-mode theory, but I think it's the full solution to the relevant quantum information task, where we are talking about single packets of light, and we're talking about single wave packets that may contain, or few wave packets that may contain the outgoing state. Imagine you want to do a photonic gate between two pulses who go out as two pulses. Did they do a C0 gate or a C phase gate? Well, probably some of the dispersive effect also make them scatter into other modes, but I'm only interested in the modes where my quantum bit is actually sitting, and then the rest is loss. So what you find by this theory is that you have loss of power, loss of intensity, loss of photons, but the states that you have occupy the modes that we calculate. The theory applies to any wave, and thanks to the question in the break, it certainly assumes Markov approximation. It also assumes linear dispersion during the propagation. The last thing can be compensated with the Markov approximation. I think this is a new challenge. There are lots of works on master equations for non-Markovian problems. I think this would be a fantastic problem to address with this theory too. So thank you for your attention.
Well, thank you very much, Klaus, for the really interesting talk. We have quite a lot of questions, so let me get started. The first one from Manuel Morgado, who asks whether it's possible to quantify the amount of information or entanglement that different pulses in your scheme can carry.
I think that the fact that we are dealing with discrete quantum systems makes it possible to use just the usual criteria we always have. Maybe I should just make one kind of warning. That is the U and the V occupation in the middle of the pulse is a little bit artificial. I mean, of course, if the physical system was actually cavities, then it would be the content of these cavities. But I'm really using those cavities as a way to describe a real pulse traveling. And of course, that pulse doesn't exist really anymore. There's the tail left, and if you wanted to talk about the entanglement between what has not hit your detector yet, it's not going to be the full Gaussian mode you should look at. Then it should be only that tail component. So that would be a different question. But I think the theory that I presented also allows us to answer that kind of question.
So there's a question on a sort of a technical and physics level combined from Alireza Saif, who asks, could you please elaborate on how you decide whether in your theory to use essentially the Lindblad operators A plus sigma minus, or separate operators of A and sigma minus. He says he understands the difference between the two and the implications, but ab initio, how do you decide which to use in describing the system here?
Yeah, so I guess, I mean, if the question is whether I should use this combination or one or the other. And in terms of master equations, these are actually, each of these Lindblad operators are associated to individually distinguishable dissipation channels. So if you can see the difference between one decay channel and all other ones, then it constitutes its own Lindblad operator. And because they are related, you could even think about it as related to a measurement process. The fact is here that photons leaving down this waveguide, I can simply not tell in any way whether they came from the system or from this one. And even in a classical optical sense, of course, the electric field amplitude here would be a sum of what this dipole emits and what this cavity here is emitting. So this relation is the input-output theory, so to speak, of the two-level system, which gives always the directly transmitted component together with the source term sitting here. It's a property of all differential equations that you have the homogeneous solution plus the source term. And as long as they're indistinguishable, then you just have to add them up like this. That doesn't mean that it's always an easy question to answer. So it was a good question. But I mean, in this particular case, it looks like this.
So we've got a couple more questions from Bill Phillips that have come in.
That doesn't surprise me.
Doesn't surprise any of us. Wonderful to have Bill questions here. So he asks, is the sequential transmission of a 2-photon state a filtering of the input mode, or would you see it as a conversion of that mode?
So sorry, was it about the photon blockade example, or was it the stimulated emission?
Yeah, in the case of having a 2-photon state. So I guess in the blockade example.
It's probably the blockade. Well,
yeah.
Yes. So it's actually a very good question. Of course, there is a conversion happening. The field who leaves the system is not in a perfect single mode with 2 photons in it. If you would write it as a 2-coordinate wave function, I mean x1, x2, then there would be a scar at x1 equal to x2, because they're not allowed to overlap and leave at exactly the same time. So you start out with this circular product state, and then you actually make this scar where the 2 photons cannot be at the same time. The point is just that taking this wave function and the one with this thin line cut through it, they have a big overlap with each other. So in quantum mechanics, it's not one or the other. There's one who has a 90% overlap with the other one. So when the photons leave, they are maybe 99% still in that same 2-photon wave packet. And the remaining 1% is because they are not exactly in that state anymore. I think you see the same in Bose condensate, where there's a little bit of non-condensate fraction, just because of the fact that atoms are not allowed to sit exactly on top of each other. But still, the Gross-Pitarevsky wave function can act as a good common wave function for everybody to a super good approximation.
So then we have a couple of things that I guess talk about having sort of large multi-mode systems again. So one question from Bill. He says he doesn't understand the idea that everything moves from left to right. If there's true spontaneous emission, whatever that means, then there's radiation going in all directions. So yes. How do you view that here?
Yes, so that is right, Bill. So thank you very much for that comment. We are actually making an assumption that the radiation can only travel to the right when it leaves the atom here, and so it's not so much. So there's a built-in chiral property that the light from the atom is not moving left. So that's a super good question, and I should have said that more clearly. I think that the point I wanted to make is the magic thing that even when you have that situation, it still looks from your Hamiltonian, who has to be Hermitian, that if you can transfer excitation from A to B, there's also a term taking it from B to A. And that term is cancelled by the damping terms. And that's the magic of this cascaded quantum system formalism. But you're right. I mean, there is an assumption that the atom can only emit to the right here.
So going on also to the sort of continuous spectrum, there's a question here, and I apologize for my pronunciation of the name, but from Inigo Luis Iguizquiza, and he asks about the difference between a flying qubit interacting with a cavity and a flying pulse with a stationary qubit. If you take a huge cavity, the spectrum is effectively continuous. So how or in what sense are they distinct?
Yeah, that's a super good question. That's exactly right. That as soon as you have a very large cavity, you have frequency modes being very close. And in that situation, you also have to use a multimode description. It's definitely possible for a 2-level atom to interact with several modes, and when the coupling is strong enough, and therefore you can also transfer energy between these modes. And of course, if it's just a few, then you would make a picture of it where you just have photons being in the superposition of different modes. But such superpositions of different modes can also look like a wave packet. So therefore, in the continuum limit, that superposition will actually be a wave packet. I remember a beautiful talk years ago from somebody who had a 2-level system in the middle of a big cavity, and the decay was actually coupling to these discrete modes. And what you saw was that there was just a wave packet of light, and a little while later, of course, the wave packet came back and re-excited the atom. So that's a good question. It's absolutely right. You also retrieve the full complexity of many modes when you go into that regime.
So there's another question from B. Prasanna Venkatesh, who says that from the talk, it looks like the spatial position of the cavity from which the pulse emerges as at the location of the emitter, asks if you can use this theory when the emitter is separated by a length comparable to the peak wavelength of the pulse. Essentially,
Yes.
the question of the separation between the between the emitter and the spatial position of the cavity.
Yes, and so thank you very much for that question. It's also related actually to my little omission that Bill caught a little while ago. Since there's no reflection and light being sent backwards from the system, then light is only propagating from left to right. And it's almost standard in quantum optics actually to ignore these distances. When I do detection of light from an atom, if my detector is a foot away from the atom, I'm actually detecting the clicks a nanosecond after the atom decayed. This is even puzzling because since it's the click who makes the atom decay, I actually made it click go to the ground state in the past. So light propagating in only one direction and being non-dispersive, this simple translation does not cause a problem. It's also not a problem that the pulse is much larger than the physical system. It's not a problem that, I mean, these pulses will be maybe microsecond longs because the bandwidth in this picture may be megahertz. And a microsecond pulse is 300 meters. So of course, in most labs, the pulse is actually not even finished being created before it hits the detector on the other side. And that is not a problem. And it was already part of the Gardiner and Carmichael theories also for the cascaded quantum system, that you don't have to do that. I use it to my benefit that I can actually put my artificial cavity all the way up to the qubit. So I don't have any propagation to take into account. But apart from the time delay, it's the same thing as putting it a kilometer away.
So thank you very much for that, Klaus. And I think that that's all that we have time for sort of directly in the live session. As Sebastian mentioned at the very beginning, Klaus has kindly agreed to answer the rest of the questions that you posted in the chat. And we have quite a number of them in a written form later that we'll post on the Quantum Science Seminar website. But for now, thank you very much again, Klaus, for the wonderful talk. It's very interesting. I enjoyed it very much.
Thank you, everybody.
Yeah, thank you, Klaus, and thank you, Andrew, for all the great questions. So I would like to just announce that next week we will have Kangwen Ni, who will talk about molecular quantum systems. And to remind you, if you want to get notified of all the updates, please go to our website, quantumscienceseminar.com, and subscribe to the email list and the Google Calendar. You should also check out our sister seminar, the AMO seminar, where tomorrow there'll be another theory talk by Vedika Kemani. You should certainly see that. And would like to thank you for your interest and hope to see you again next week. And as Klaus requested, we should all show our faces. So maybe we can try doing that real quick by switching here to gallery view. Then you can maybe see all of us. And thank you again, Klaus. Thank you everyone on the team for helping out. And I'll see you all next week.
Bye-bye.